Hello everyone. Today we will learn about Cauchy sequence and Cauchy's general principle of convergence. Cauchy sequences. Definition 1. A sequence Sn is called a Cauchy sequence if for each epsilon positive there exists a positive integer m such that modulus Sn minus Sm is less than epsilon for all n greater than or equal to m. The above definition can be rewritten in the following two equivalent forms. Definition 2. A sequence Sn is called a Cauchy sequence if for given epsilon positive there exists a positive integer m such that modulus Sn plus p minus Sn less than epsilon for all p greater than 0. Definition 3. A sequence Sn is called a Cauchy sequence if given epsilon positive there exists a positive integer m such that modulus Sp minus Sq is less than epsilon for all p q greater than or equal to m. Cauchy sequence examples. The sequence Sn is equal to 1 by n is a Cauchy sequence. Let epsilon be positive, p given, and let n is greater than m and Sn is equal to 1 by n. Now modulus Sn minus Sm is equal to modulus 1 by n minus 1 by m is equal to 1 by m minus 1 by n. As n is greater than m, therefore 1 by m is greater than 1 by n. And therefore this modulus will become 1 by m minus 1 by n. Thus modulus Sn minus Sm is less than 1 by m less than epsilon if m is greater than 1 by epsilon. Let m be a positive integer such that m is greater than 1 by epsilon, then modulus Sn minus Sm is less than epsilon for all n is greater than or equal to m. Therefore, by definition of Cauchy sequence, the sequence Sn is equal to 1 by n is a Cauchy sequence. The sequence Sn is equal to n square is not a Cauchy sequence. How we will show this, why it is not Cauchy sequence? Let Sn is equal to n square, p is equal to twice m plus 1 and q is equal to twice m, so that p q greater than m. Then modulus Sp minus Sq is equal to modulus p square minus q square is equal to p plus q into p minus q is equal to modulus 4m plus 1, which is greater than 1 for all m belongs to n, because m is natural number. If epsilon is equal to half, it is not possible to find any positive integer m such that modulus Sp minus Sq is less than epsilon for all p q greater than m. Hence, the sequence Sn is equal to n square is not a Cauchy sequence. Theorem: every Cauchy sequence is bounded. Proof: let Sn be a Cauchy sequence. For epsilon is equal to 1, there exists a positive integer m such that modulus Sn minus Sm is less than epsilon for all n is greater than or equal to m. Implies that Sm minus 1 less than Sn less than Sm plus 1 for all n greater than or equal to m. Let k is equal to minimum of S1, S2 up to Sm minus 1, Sm minus 1, and capital K is equal to maximum of S1, S2, Sm minus 1, Sm plus 1. Then this sequence is bounded by k and small k and capital K. That is, small k is less than or equal to capital Sn less than or equal to capital K for all n belongs to n. Therefore, the sequence Sn is bounded. Hence, every Cauchy sequence is bounded. But converse need not be true. That is, the converse of the above theorem need not be always true. That is, every bounded sequence need not be a Cauchy sequence. For example, let Sn is equal to minus 1 raised to the power n is equal to minus 1 plus 1 minus 1 plus 1 is bounded as minus 1 less than or equal to Sn less than or equal to 1 for all n belongs to n. Let Sn is equal to minus 1 raised to the power n. We now show that Sn is not a Cauchy sequence. For this, let p is equal to twice m plus 1 and q is equal to twice m, so that p q is greater than m. Now, modulus Sp minus Sq is equal to minus 1 raised to the power twice m plus 1 minus 1 raised to the power twice m equal to minus 1 minus 1, this is equal to 2. So, modulus Sp minus Sq is equal to 2. If epsilon is equal to half, then it is not possible to find any m belongs to n such that there exists a positive integer m such that modulus Sp minus Sq less than epsilon for all p q greater than m. Because modulus Sp minus Sq is equal to 2, and if epsilon is equal to half, then this condition will not be satisfied by the sequence. Hence, the sequence Sn is not a Cauchy sequence. Therefore, the sequence Sn is bounded but not Cauchy. Therefore, converse of the theorem every Cauchy sequence is bounded is not true always. This is the statement Cauchy's criteria for convergence. A sequence converges if and only if it is a Cauchy sequence. That is, a sequence converges if it is Cauchy sequence, and conversely every Cauchy sequence is converges. that is, if a sequence is a Cauchy, then it is convergent. Cauchy is general principle of convergence. Theorem 3. A necessary and sufficient condition for the convergence of a sequence Sn is that for each epsilon positive there exists a positive integer m such that modulus Sn plus p minus Sn is less than epsilon for all n is greater than or equal to m and p is greater than or equal to 1. Necessary condition. Suppose that the sequence is convergent and let L be its limit. We have to show that for each epsilon positive there exists a positive integer m such that modulus Sn plus p minus Sn less than epsilon for all n is greater than or equal to p and for all n greater than or equal to m and p is greater than or equal to 1. Since the sequence is convergent, so for a given epsilon positive there exists a positive integer m such that modulus Sn minus L less than epsilon by 2 for all n is greater than or equal to m. If p is greater than or equal to 1, then n plus p is greater than n is greater than or equal to m. And so modulus Sn plus p minus L less than epsilon by 2 for all n is greater than or equal to m and p is greater than or equal to 1. Therefore, modulus Sn plus p minus Sn is equal to modulus Sn plus p minus L plus L minus Sn less than or equal to modulus Sn plus p minus L plus modulus L minus Sn, which is less than epsilon by 2 plus epsilon by 2 is equal to epsilon for all n is greater than or equal to m and p greater than or equal to 1, which proves the necessary condition. Now converse part or sufficient condition. Suppose that for each epsilon positive there exists a positive integer m such that modulus Sn plus p minus Sn less than epsilon for all n is greater than or equal to m and p greater than or equal to 1. We have to show that the sequence Sn is convergent. For this, first we show that the sequence is bounded and that it converges to a limit. Now, by the given condition for epsilon is equal to 1, there exists a positive integer m0 such that modulus Sn plus p minus Sn less than 1 for all n is greater than or equal to m, 0 and p is greater than or equal to 1. In particular, for n is equal to m0 modulus s m0 plus p minus sm0 less than 1 for all p greater than or equal to 1. That is sm0 minus 1 less than sm0 plus p less than sm0 plus 1 for all p greater than or equal to 1. Let g is equal to minimum of s1, s2, sm0 minus 1, sm0 minus 1, capital G is equal to maximum S1, S2, Sm0 minus 1, Sm0 plus 1. Then G less than or equal to Sn less than or equal to capital G for all n. Hence, the sequence is bounded. Hence, the sequence is bounded, and therefore, by Bolzano-Weierstrass theorem, for sequences, it has at least one limit point, say L. We shall now show that the sequence converges to L, that is, limit n tends to infinity Sn is equal to L. Now, by the given condition, for epsilon positive, there exists a positive integer m such that modulus Sn plus p minus Sn less than epsilon by 3 for all n greater than m and p is greater than or equal to 1. In particular, for n is equal to m, modulus Sm plus p minus Sm is less than epsilon by 3 for all p greater than or equal to 1. As L is a limit point, there exists an integer m1 greater than m such that modulus Sm1 minus L is less than epsilon by 3. Also, since m1 is greater than m, therefore from 1 we have modulus Sm1 minus Sm is less than epsilon by 3. Now, combining these three conditions, we have modulus Sm plus p minus L is equal to modulus Sm plus p minus Sm plus Sm minus Sm minus 1 plus plus Sm1 minus L, which implies that modulus Sm plus p minus L less than or equal to Sm plus p minus Sm plus Sm minus Sm1 plus Sm minus Sm1 minus L less than epsilon by 3 plus epsilon by 3 plus epsilon by 3, which equals epsilon for all p greater than or equal to 1. Therefore, modulus Sn minus L is less than epsilon for all n greater than or equal to m. Hence, the sequence Sn converges to L, which proves the sufficient condition for the Cauchy's general principle of convergence. Now, some examples. Example 3, show that the sequence Sn is equal to 1 plus half plus 1/3 up to 1 by n cannot converge. Solution: suppose, if possible, the sequence Sn is convergent. Let us take epsilon is equal to half, n is equal to twice m, p is equal to m in Cauchy's general principle of convergence, so that modulus S twice m minus Sm is less than epsilon by 2, but S twice m minus Sm is equal to 1 plus half plus 1 by m plus 1 by m plus 1 up to 1 by twice m minus 1 plus half plus up to 1 by m, which implies that Sm S twice m minus Sm is equal to, these terms are cancelled up to 1 plus half plus 1 by m. These terms are cancelled by these terms. Therefore, S twice m minus Sm is equal to 1 by m plus n plus up to 1 by twice m, which is greater than 1 by twice m, because this term is always greater than 1 by twice m, and in this way this quantity is greater than 1 by twice m plus 1 by twice m plus up to 1 by twice m times, which is equal to m by twice m is equal to half. Therefore, S modulus S twice m minus Sm always greater than half in this case, which contradicts Cauchy's general principle of convergence, because this condition is not satisfied. Therefore, the sequence cannot converge. Example 4. Show that the sequence Sn is equal to minus 1 raised to the power n by n is a convergent sequence. Solution: let epsilon be positive be given. Let n greater than m. Now, modulus Sn minus Sm is equal to minus 1 raised to the power n by n minus 1 raised to the power m by m, which is less than or equal to minus 1 raised to the power n by n plus minus 1 raised to the power n by n is equal to 1 by n plus 1 by m less than 1 by m plus 1 by m is equal to 2 by epsilon if m is greater than epsilon by 2. We know that modulus a plus b is always less than or equal to modulus a plus modulus b. This condition is followed. Therefore, modulus Sn minus Sm is equal to 2 by m less than epsilon if m is greater than 2 by epsilon. Thus, for each epsilon positive, there exists m in n such that modulus Sn minus Sm less than epsilon for all n greater than or equal to m, where small m is greater than 2 by epsilon. Hence, the sequence Sn is a Cauchy sequence, and so by Cauchy's criteria of convergence, Sn is convergent sequence. Example 5. Show that sequence Sn is equal to 1 plus half plus 1/3 plus 1 by n is not a Cauchy sequence. Suppose, if possible, the sequence Sn is convergent. Let us take epsilon is equal to half, p is equal to twice m, q is equal to m, so that p q greater than or equal to m. So, modulus Sp minus Sq is equal to modulus S twice m minus Sm is equal to this quantity 1 plus 1/3 up to 1 by twice m plus twice m minus 1 plus half plus up to 1 by m, which equals 1 by twice m plus 1 plus 1 by twice m plus 3 up to 1 by twice m plus twice m minus 1 m times is greater than 1 by twice m plus twice m plus 1 by twice m plus twice m up to 1 by twice m plus twice m times is equal to m by 4m is equal to 1 by 4. Thus, modulus s twice m minus sm is greater than 1 by 4 for all p q greater than or equal to m. Hence, if epsilon is equal to 1 by 4, it is not possible to find any positive integer m such that modulus s twice m minus sm is greater than 1 by 4 for all p q greater than or equal to m. Hence, the sequence is not a Cauchy sequence, and by Cauchy's criteria of convergence, Sn is not convergent.